Okay, in this recording, I'm going to go through one of the homework problems from chapter 7, having to do with the sample mean and sampling error. So here's the problem right here. I have it printed out. And let's make this there. Okay, I have it printed out right here. So it's looking at the data on salaries in the public school system, which are published annually by a teachers association. The mean annual salary of public classroom teachers is 57.7 thousand. So you may have gotten slightly different numbers when you did this problem, but these are the ones that came up for me. It says assume a standard deviation of 8.4 thousand and then complete parts A through E. So first it says determine the sampling distribution of the sample mean for samples of size 64. So you take samples of size 64. You're going to get a sample mean every time you take one of these samples of size 64. And this sample mean, this X bar, is going to have a distribution. The mean of that distribution, so the mean of X bar, is going to be the mean of the population. This equation is given to you on your equation sheet. So that part's not bad. That's going to be the 57.7 thousand, and I'm just writing it out the long way in the thousands. The standard deviation of the sample mean, right here, the standard deviation of X bar, is going to be that equation also on your equation sheet, which says that the standard deviation of X bar is simply the standard deviation of the parent population divided by the square root of n. In this case, n is 64, so it's the square root of 64. And the standard deviation of the parent population is that 8.4 thousand. Okay, so we have 8,400 divided by the square root of 64, which is, of course, 8,400 divided by 8, and that ends up to be 1,050. That's supposed to be a 0 there. Okay. Next, once we have the mean and the standard deviation, we have to decide if we can actually draw the picture for this distribution or not. So the question here is it approximately normal or is it unknown? Those are basically the only two cases for us at this point. And the answer is it's approximately normal. The reason we know that is because the sample size we're using is 64. And by the central limit theorem, we know that for any sample size greater than 30, greater than or equal to 30, we can assume that X bar is at least approximately normal. I'm going to fix this 0 here. There we go. So it's going to be approximately normal. Then the problem goes on, it asks the same information, except it changes the sample size now to 256, So what's going to change? Well, the mean's not going to change. That's still going to be the mean of the given population, of the parent population. The standard deviation will change now because n is used in that equation. So now it's going to be the 8,400 from the parent population divided by the square root of 256, which ends up to be 6, square root of 256 is 16. So now you have 8,400 divided by 16, and that ends up to be 525. So our standard deviation has been cut in half. We have a smaller standard deviation. This intuitively should make sense to you because as your sample size gets larger, the standard deviation of your sample mean should get smaller. Why? Because your sample mean, each individual X bar that you calculate should be clustered closer to the mean because our sample size is getting bigger. We're approaching the size of the population, which means we're going to get better estimates. The larger our sample size, the better our estimates are going to be, the better our sample means are going to be. So my X bars, when I use a sample size of 256, my X bars are going to be closer to the mean. Intuitively, we should understand that, but then also algebraically, we kind of have shown it here because our standard deviation for the 256, size 256, is smaller than the standard deviation when we had a size of 64. And of course, for 256, that's also going to be approximately normal because 256 is certainly much, much bigger than 30. And 30 is the number that the central limit theorem says we have to get to. So now the next part of this, so then it asks, when you decided that these two distributions, these two X bar distributions were normal, did you have to make any assumptions about the parent population? In other words, did you have to assume the parent population was normal? And the answer here is no. We did not have to make any assumptions about the distribution of the parent population because our sample sizes were both greater than 30. So that answer would be B. So the only time you have to worry about the distribution of the parent population is when you have small sample sizes less than 30. Okay, so now we get into the part of the question that was a little confusing for a lot of you. Part D, for samples of size 64, what is the probability that the sampling error made in estimating the population mean salary of classroom teachers by the sample mean will be at most 1,000, will be at most 1,000. Then, so it has you do that, okay, and then it has you do the same thing, for the sample size at 256. So I wrote this out on the board. I'm going to do this on the board behind me. I'm going to stop sharing this, and we're going to do this out now on the board so that, hopefully it's not stop shaking, okay. On the board so that, we can do it together, and hopefully you can see it a little easier. So I wrote this out ahead of time. So for samples of size 64, what is the probability the sampling error made in estimating the population mean salary of classroom teachers by using the sample mean will be at most $1,000. So the first issue with doing this is trying to understand what the heck they're asking here. What are they asking? Basically, what they're asking here is if we use the sample mean, if we use X bar to estimate our population mean, so it's the population mean, we're trying to estimate the population mean salary of classroom teachers, right? So if we use X bar to estimate that, what's the probability that our sampling error will be within 1,000? Within 1,000 of the population mean that we're trying to estimate. So you have to, so if you draw your picture of X bar, where the mean of X bar, of course, is the mean of the population, it's asking, what's the probability I'm within 1,000 of that? That's what it's asking. Remember, this picture of X bar here is basically a picture of sampling error because every X bar is an estimate of the mean. So any X bar that's not exactly right on the mean, so if you deviate from the mean at all, you have sampling error. Sampling error. The farther you deviate, the bigger your sampling error, right? So in this case, we specifically want to know what is the probability that we have a sampling error of 1,000 or less. So we have to, we're trying to figure out where does the 1,000 sort of come down here? Where does it lie? Well, let's fill in our numbers for this distribution. We already calculated them. In the first part of the problem, we calculated them over here. We know the mean, when we have a sample size of 64, we know the mean is 57,700. We know the standard deviation is 1,050. So to figure out what this mark is here, I just add 1,050 to it here, and I get 58,750. If I add another 1,000, I get 59,800, 60,850. If I go on the other side, 56,650, 55,600, and then 54,550. So these numbers I just got by, adding 3 standard deviations above. So I start, here's my mean right here, and then I added 1,050 to get this number, add it again. That's where these numbers come from. Why am I drawing out all these numbers? So then it's a little easier to see where the plus or minus 1,000 comes in. So we want to know what the probability is that the sampling error is at most 1,000. That is asking what's the probability that I am plus or minus 1,000 from the mean. That's what it's asking. I could draw a line down the middle here. So if we add 1,000, so 57,700. If we add 1,000, we'll get to 58,700. So just below this first standard deviation here is where we're going to land. So let me fill that in here. So if we add 1,000, right, we're going to end up just below this guy here. I'm not drawing it quite straight, but the larger X bar here, when we add the 1,000, that's going to be 58,700. That's where that one's going to land. I just added 1,000 to the mean that I started with. When you subtract 1,000, you're going to end up down here. Okay, and this point here is going to be, that's the lower X bar, right? That's going to be 57,700 minus 1,000, so 56,700. That's where that point is going to be. The probability we're interested in is this, because this is 1,000 away right here. Anything inside of there is less than 1,000, right? And in the other direction, this is 1,000 away, and anything less than that going this way covers all of this area here. So this area in the middle, all of these points here have a sampling error of 1,000 or less. So it's 1,000 or less it goes in. And the way you can say that is you could say 1,000 or less, or you could say at most 1,000. But this is what the question is asking. This is the probability that I'm looking for. If you draw this picture correctly, 95 out of 100 times, you'll probably get the answer correct. So moving from here, now we have to find this probability. How do we do that? Well, we're going to have to convert these two X bar values to Z values, find the probability of each one of those, and then subtract those probabilities to get the probability that we need. So I'm going to erase this part at the top here so that I can leave my picture and we can do those calculations. Okay. So let's get Z2 first. That's the bigger one. So we want to convert this X bar here to a Z value so that we can look up the probability. So this is going to be X bar, let's call it X2 bar, right? Minus the mean over the standard deviation. So it's going to be 5,8,700 minus the mean. There's something you'll notice pretty quickly. Divided by the standard deviation of X bar. So for this particular one with the size 64, remember the standard deviation was 1050. This is going to equal, when you subtract these, not surprisingly, right? You're going to get 1,000. And then the final calculation is 0.95. When you are looking at sampling error, you're always looking at the deviation from the mean, from the center. So when you do this out, this is the part here that ends up, this is where the 1,000 ends up. Because the high end of your sampling error is going to be 1,000 above. That's your max sampling error that you're going to. So unsurprisingly, the guy in the bottom, this Z1, he's 1,000 below from the mean. So when you do the calculation for the Z1 and you plug in X1 bar, right, you're going to get 56,700, right, minus the 57,700 over 1050. That's going to give you a negative 1,000 because it's 1,000 below, which not surprisingly gives you a negative 0.95 for the other Z value. And if you intuitively had figured that out ahead of time and you took that shortcut and went right to this step, that's fine. But I want you to know where those numbers are coming from, because I could tell some of you are confused about where do you put the 1,000? How does 1,000 come into play there? Well, the 1,000 comes into play because that's where the X1 bar and X2 bar are going to be located. 1,000 above and 1,000 below. So now that I've gotten these two Z values, I can finish it up and get the probability. Because the final probability will be the probability of the larger Z minus the probability of the smaller Z. And in this case, when you look these two up, when you look up 0.95, we get 8289. And when you look up negative 0.95, we get 0.1685. And when you subtract those two, we get 0.6604. That is the probability that the sampling error will be at most 1,000 when you have a sample size of 64. So in other words, this is the probability that X bar will be within 1,000 of the mean you're trying to estimate. This is the probability that X bar will be within 1,000 of the mean that you're trying to estimate. Remember, this is the guy you're trying to estimate. You're hoping all your X bars will be right here, but of course they won't be. Okay. Now the problem wants you to find this same probability, except for the sample size of 264. 264, is that right? Yeah. 256, sorry, 256, not 264, 256. So what will change in this calculation? Well, what happens is when we increase the sample size, remember the standard deviation changed. So the picture here is going to change a little bit. Let's see how the picture is going to change. And you know what, I'm going to leave most of this up here. I think I might be able to. Well, you know what, there we go, leave it like that. Okay. This is going to change, obviously, probability. All right, so how will the picture here change? Let's see. Here I drew 3 standard deviations above and below. Well, my standard deviation was 1050 at that time. Now, for the new problem, and I'll use green for this one, when n equals 256, we found that the standard deviation was 525. Okay, so what would that look like on here? So let's see. 525 above is going to be right here. Okay, and then you add another 525, you'll end up here, and another 525, you'll end up right here. On the other side, subtract 525, you'll end up here. Another one, you'll end up here, and another one, you'll end up here. So for this second distribution, 3 standard deviations above and below is these 3, you know, these green tick marks here. And if I'm trying to draw the picture to scale, I'll try the best I can. It's going to be, instead of being spread out like this, now it's going to be squished in more. It's going to be taller and narrower. So let's see how I do here. This is kind of difficult, but I will try my best. Okay, not bad. Actually did pretty good there. So the new distribution, because I just squished it in tighter, whenever you squish it in, it's got to pop up because it still has the same area, okay? So I squished it in. Now, the 1,000 mark, okay, is still going to be right here because I drew it to scale. It's going to be right there, except now it's covering this part too. So now it covers all that green part there. So intuitively looking at that, you should be like, oh yeah, that probability is going to be bigger. I just covered in a whole bunch more stuff here, okay? So let's figure out exactly what it will be. So looking up here at our equation now, we're going to be like, okay, well, what's x2 bar? Well, it's still going to be right at the same spot, 5770, so it's going to be 58700, right? And this spot right here is at 56700. This is x1 bar, and this is x2 bar. Okay. So x2 we're doing, so this again is that 58, right, 700 minus the mean. The difference is now we're dividing by the new standard deviation, this 525. So now it's going to be 1,000 divided by 525, which equals 1 point something. Where is it? 1.90. So now Z2 is 1.90, and I could do the same thing for Z1, but I think you can guess it's going to turn out to be negative 1.90 because it's the same distance below as the other guy was above. So I don't have to write it all out, but you could obviously. And you get, so these are now my 2 Z values. And the probability we're looking for is still going to be P2 minus P1, except now our probabilities are going to be different, right? Because our Z's are different. P2 minus P1. So now the new probability will be, when we look up 1.90, we get 9713. And when I look up a negative 1.90, I get 0.023, 87. 0.287, and then you subtract those two, and the probability that we're within 1,000 is now 9426. Much bigger. The last one was for the previous sample size. So this one is for 256. This is the probability for 256. The probability when we had a size of 64 was 0.6 something. Where is it? 6604. So it went up considerably when we increased from a sample size of 64 to 256. The probability that our X bar was within 1,000 of the mean went up by almost 30%. Why? As we increase the sample size, the standard deviation gets smaller. The X bar values are going to cluster closer to the mean, like this green distribution is here, the green one. Okay, the X bars are clustering closer to the mean. So the probability that you're within a certain distance of that mean, in this case 1,000, is going to increase compared to when the sample size was smaller. So that's what that problem was, trying to get home to you.